Okay, well, I can see we just hit 1 minute after the hour, so I'm going to go ahead and get started. My name is Matt Thomas, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and co-organized with contributions from Stephen Slaughter and Jamie Kostelnik. I'd also like just to announce that there are going to be some changes coming to our seminar committee, which are quite exciting. John Perkins from the USGS Geology, Minerals, Energy, and Geophysics Science Center is going to be taking over the coordinator role for the seminar in January 2025. And Shelby Arendt from the USGS Geologic Hazard Science Center here in Golden, which is where I am, is also going to be assisting with our seminar committee. So I look forward to seeing those changes in the new year and some new faces and perspective on the seminar. So for those of you that are new to this meeting, you have the ability to submit questions via the chat window or to use the raise your hand feature in combination with your microphone or video camera. We're going to wait until the end of today's presentation to take questions. So in the meantime, please just do the best you can to make sure your microphone is muted when you're not intending to speak. It's my pleasure to introduce Bill Burns. Bill is an engineering geologist with the Oregon Department of Geology and Mineral Industries. He earned his bachelor's degree in geology at Florida State University and his master's degree in geology at Portland State University. He's the principal investigator at Dogami on landslide hazards and has authored many publications on landslide hazard mapping methodology, risk analysis, and mapping. He spent the last 25 years helping communities in Oregon understand and reduce risk from landslide, earthquake, and volcano hazards, and I can say that we're very lucky to have him here today. So Bill, with that, I'm going to go ahead and let you take it away.
Great. Thanks much, Matt. And thanks for having me. And thanks for having the seminar. We were just talking about how fantastic this is, all these talks. So I'm really excited to share with everyone today some research that we've been doing in Oregon using multi-temporal lidar to better understand landslide and debris flow hazards in Western Oregon. And really want to recognize kind of a dream team of researchers that we had on this project, including Nancy Calhoun, who's now at the Washington DNR, Marin Sanders and Josh Roaring from University of Oregon, Nick Matthews and Francis Rangers from USGS, Ben Lashinsky, Mike Olson, David DeSosa from Oregon State, and Michael Zimmerman from Oregon Department of Transportation. So I also wanted to point out that this data set has led to continued research of which Marin and David are both going to present here in this same seminar on November 20th. So look forward to that talk coming in a couple months. So little outline of what I'm going to talk about today. Start with identifying the study area and some research we did on kind of historic pre-fire debris flows that have happened in this area. Then we'll take a look at these 3 atmospheric river type storms that have impacted this area. We'll look at the LiDAR change analysis that we did, get into some findings, and then we're going to look at one debris flow in detail, the fatal Levens Creek debris flow, and then finally some summary and conclusions. So 2017, we had the Eagle Creek fire in the Columbia River Gorge, and it's very close to Portland, only 20 miles east of downtown Portland. And 3.5 years later, we had an atmospheric river storm in January 2021 kind of park over this area, and that resulted in many debris flows and very unfortunately one fatality. And all of this together kind of led us to this need for kind of researching how post-fire may affect debris flows, especially in Western Oregon. And so our objective in this was to evaluate pre and post 2017 Eagle Creek fire debris flows using multi-temporal bare earth LiDAR DEMs. So here's the study area, again, just east of Portland in the Columbia River Gorge, which is a pretty unique location. You know, the Columbia River cuts across the Cascade Range here, which is very unique that a large river just cuts right through a mountain range. But the summers are really warm and dry, and very rare we get thunder showers. The winters tend to be cool and wet with occasional atmospheric river type storms between very prolonged drizzle. It rains a lot here. There's a lot of precipitation in the gorge. Most of it falls as rain, but as you get into the higher elevations up on the plateau here, which is above 3,000 feet, some of that is falling as snow up there. And, just in general, the geology and the very steep slopes that are in here leave kind of a landscape that's very susceptible to landslides, rockfall, and debris flows. So first thing we did was try to get a little bit of a handle on this debris flow prone region. So we did 3 tasks. One, we just looked at historic records, and we looked back at events that people have noted, and the earliest one we found was in 1918, but we found events, probably mostly notable events, all the way through about 100 years worth of records. Most of these are very likely just big events that impacted people or hit the highway or something like that. And come up, if you annualize this, you get about 1 per 10 years, 1 per 20 years kind of thing. Next task we did was we have 30 years worth of orthophotos in this area. So we took those and used those to map this area. And we found 155 debris flows that occurred in here. These are all pre-Eagle Creek fire. And you can see those numbers down here. And if you annualize these, you get about 6.5 debris flows per year. And this should really be considered kind of a long-term background rate, right? Because when we map with orthophotos, we know we don't always capture every single event. In fact, we know there was a huge event in 96 that caused many, many debris flows, and our numbers are not that big for that. And what that means is we probably just couldn't see them all in the orthophotos. But at least it's kind of a long-term background, right? Third thing we did was use all that great lidar data that we have in there to do fan mapping. You can see all these fans in here. Some are along the Columbia. Some of these larger drainages that go further back up, the fans are located at the mouths of these tributaries and not down here at the mouth of the drainages. So just by the way, this location here in Dotson, Warrendale is on the cover of the USGS Debris Flow Hazards in the U.S. Fact sheet. That's this location, and this event happened in February 96. So let's look at those 155 pre-fire orthophoto debris flows a little closer. One thing we did was we tried to estimate the initiation style of these. They're in, photo, so it was difficult to do, but we did at least estimate, and we put them into these 4 categories: deep landslides, shallow landslides, what we're calling in-channel initiations, and then runoff generated. And you can see down here, most of these were initiating by shallow landslides. And then second runner-up was these in-channel type failures. And then we had very few runoff and very few deep landslide initiations. Well, let's look at this a little closer. Now, these aren't the orthophotos, but this is examples of these. You can see these are shallow landslides. Here's one. Oh, so what I'm going to be showing here in this LiDAR change, everywhere I was showing is red is going to be where the ground has moved down, and blue is going to be where the ground has moved up. So here's a shallow landslide that really didn't end up taking off as a debris flow. Here's another one. I don't know if you can see the channel, but the channel kind of comes down there and then wraps around. You can see this initiated kind of on the banks of that channel as a shallow landslide entered the channel, actually deposited a little, and then kind of kept on going and coalesced, or happened at a different time with this bigger debris flow track here. These 2 down here are examples of what we're calling in-channel initiation. So above which, what we kind of see is erosion in the channel. And then at some point, the entire channel seems to be, the entire bed of the channel seems to fail. And then below that, it really looks like debris flow tract. And let's look at those a little closer so that we can kind of examine this a little bit. So here is, we're going to look at this photo of this box right here over on the left-hand side. So up above, the initiation is kind of right in here, and there's a waterfall sitting in here, but up above it, it kind of looks like maybe erosion in the channel. And below that, I don't know if you can see that, but the entire channel really looks like it's been scoured out. And I'll just draw some yellow lines here so that you can see what I'm talking about. It's almost like there's a headscarp right here, and then below that, there is nothing but kind of debris flow track that takes place. So because all of this is digital data, it's really easy for us to just draw cross sections. So I drew a couple here. This lower one here is up in here, up in the area that we're calling erosion in the channel, pre-initiation of the debris flow erosion. And you can see the before is in blue and the after is in orange. You can really see it looks like there's kind of this downward erosion happening, kind of grain by grain. It still leaves these very angular shape of the channel. But if you look down here at the cross section, again, before is in blue, orange is after. You can see like the entire channel seems to be scoured out after this debris flow came through. It just took all the material kind of with it. And just another photo. This is from this photo is further down this channel where this cross section was taken, kind of down here. And you can really kind of see in the photo that looks like it's a kind of this U-shaped where the debris flow has passed through this area. Okay, so let's look at what happened. So 2017, this is before the fire on the left. This is after the fire on the right. You know, the big thing to notice is the vegetation is extremely dense in Western Oregon. There are giant trees just all over the place. And the only places without trees are these steep rocky outclaps or in places where landslides have happened recently, like this one that came down this channel. But over here, the other thing to notice is that all the trees are still standing. They're all dead, but they're still kind of standing upright. So let's take a closer look at what this looks like on the ground. These two examples are not from Eagle Creek, but they're really similar looking to Eagle Creek. So this is kind of what Western Oregon looks like on the left. We have this very dense, thick forest floor with tons of organics. Then we have this very brushy understory, which makes it extremely difficult to do field work in some cases, especially if they're blackberries with pricklers on them. And then above that, we have these giant trees that go way up into the air with a very dense canopy up there. So over here is after a fire. This is actually in the Holiday Farm area. But the main thing to notice is, well, all of this understory and forest floor are gone. We're down to the mineral, the colluvium on the forest floor here. In some cases, you can see these beautiful little colluvial wedges behind these trees. Main thing is, though, all the trees are still standing. And as you can imagine, if you were water and you rained on this area, it'd be really hard to find kind of a nice straight path for that water to flow down. It would probably have to kind of meander its way around all these trees, which may be part of the story that we're trying to discover here. So let's look at these storms that have impacted this area. Again, we had three kind of atmospheric river type storms. This was the first one right after the fire in January 2021 was rated as strong to extreme. You know, it really lasted for at least 2 days straight. You can kind of see that on the weather station that we have in the Portland West Hills that tracked this thing as it was crossing. This is what that atmospheric river looked like. There's Oregon outlined in black, and that green dot, unfortunately, is where the Eagle Creek fire was. And you can see it's right down the center line of this atmospheric river coming in. So we had these three storms. Over on the left are the storms and then the LIDAR data that was collected in between or after these storms. So we had the 96 event, and very unfortunately, we did not have LIDAR before the 96 event, or we could do kind of a more direct apples to apples comparison of pre-fire to post-fire. So we didn't have that, but we tried our best to do this comparison. So we have LIDAR collected in here at 09. We had the fire. LIDAR collected again. We had a big storm with debris flows. LIDAR collected again. Another storm and another set of LIDAR. And over here on the right, you can see these three storms. I we kind of normalize these to 0 in October. The dashed dotted line is kind of our 30-year average in here. And you can see the 96 year, which is in blue, was quite a bit above that average. And where that storm took place, the antecedent, the amount of rainfall we had during that winter was quite a bit higher than either of these storms that we're going to look at in a little more detail. This is the January 2021, and you can see, we had almost half the rainfall in both of these cases than we did in 96 when that storm had happened. So let's look at these storms a little closer. So up at the top, there's a table with the 3 storms on there. We have that antecedent, kind of seasonal antecedent that I was talking about. We also had, in some cases, quite a bit of snowmelt. When these atmospheric rivers come into Oregon, they not only bring a lot of moisture, but they bring very warm air. And you can see that in the temperature change. Here in 96, it went from quite a bit below freezing to quite a bit above freezing very quickly. And sometimes if there's a lot of snow on the ground, that can melt, and that snow adds into that terrestrial water input, added in with the rainfall, and then you get this kind of total terrestrial water input. One thing about the 96 event, well, it was a lot of water, and we ended up with very widespread kind of 100-year flooding across most of Western Oregon in that case, compared to these other events. Down here on the bottom, you can see these graphs of the snow melt that's down here on the bottom and the rainfall and how those combine to push this curve up. And then you can see kind of the onset of the debris flows that happened. So we did a couple things, regarding water. One thing we looked at was Tom Wiley over here used the 96 storm event, and he estimated how much rainfall it took in a 24-hour period to trigger debris flows. And in this area of the gorge, he came up with about 6.5 inches in 24 hours. If you see that much rain, it's likely to have debris flows being initiated. Now, he only used one storm to do this, and so as you can imagine, and it was a really big storm, so as you can imagine, this threshold is probably at the upper ends of the threshold. So one thing we did was we tried to examine that. We used these 155 pre-fire debris flows. We used PRISM data to look at, hey, what was about the 24-hour rainfall on the days that we estimated all of these occurred? And we came up with a bigger range, 1.5 to 9 inches in 24 hours, but a mean of 4.7 in 24 hours, which is quite a bit less than Wiley's mean up here. And then finally, we can look over here. So one thing we looked at was before these events, we just looked at the 24 hours before these events. So for example, January 21, down here at 0, if you look back, the 24 hours would start somewhere about here and then count up to here. So in January 96, we had about 9 inches of rainfall before the events, before the debris flow started. And when they did, we had lots of them and many big ones. January 2021, we had about 8 inches of terrestrial water input, and lots of them in big. January 2022, about 5 inches, and these were kind of small to medium. So they kind of are relative to each other. Okay, so now let's dig into the LiDAR data sets. So we had 4 LiDAR data sets. With that, you can create 3 change data sets. The first one, again, 09 to 018. This was collected right after the fire. We really don't think there was any events, like we didn't hear about any events that happened. So we really think this whole change epoch, the 9-year one, is mostly pre-fire. Then we have this data. We have a storm in January 2021. So we have another epoch in here that's post-fire, 3 years. And then finally, one more change data set down here that's only 1 year and surrounds this 2022 storm. We also had a lot of other great information that helped us. For example, lots of NAPE imagery. ODOT flew helicopters after storms, and I showed you some of those photos just a second ago. And we also did a lot of field work after storms in here. So after you get all this LiDAR, first thing you need to do is kind of do some processing and establish some thresholds. And our LiDAR data sets ran over a 13-year period, which is a pretty long time when we're in this kind of rapidly evolving technological revolution that we're in, right? Lots of advances in LiDAR collection and processing and all of that. And so we were very fortunate that we had Professor Mike Olson from Oregon State University, who is an absolute pro at processing LiDAR data sets. And he helped us by reprocessing some of the earlier data sets, going back to the point clouds, adding in more ground points so that our ground point densities were more similar to these later data sets. The other thing you got to do is establish thresholds of change, right? If you don't have a threshold at all, your change data set may look something like this, and it's really hard to see where events are happening. Everything looks like it either went up or down. If you use too big of a threshold, well, you're going to miss some stuff. And if you use just the right threshold, you're going to get stuff that looks like this and really be able to see these events. In this case, this is a path of a debris flow coming across the fans. We have erosion in red. We have these beautiful debris flow levees in blue being deposited along the edges of this thing. And this is one of the orthophotos, or sorry, ODOT helicopter photos of this exact location. You can see this beautiful levee on this side, large woody debris and boulders and such. And then the path where all the scour took place in here, and then another debris flow levee being developed on this outside path here. So how do we do the mapping? Well, we used variable thresholds in this case, depending on the scale that we were mapping at, and here's some of those up here. Each of the polygons that we mapped, we basically attributed with 5 different fields. The primary process, which is this list down here, and then the event unique ID, so we could tie all of these polygons together, kind of a location information, the dates of difference, and some notes. And over here on the right is some examples of that mapping. So here's the LiDAR before the hillshade and the contours, and then here's the LiDAR after. And even without the change data set, you can see where this shallow landslide initiated up here in this road fill embankment. You can see initiated here, went over this little cliff, kept coming down the slope here, eroding more, and then deposited some material here in this creek below. And then if you look at this image below here, this part here is what we were just looking at. You know, either this material kept going or this creek had enough water in it to erode some of this, and a debris flow was initiated. It came down this channel, eroding in red here. As it went around this corner here, it looks like it was depositing material, maybe slowing down. And then it kept going. Down here, we had kind of mixed erosion and deposition, and then it probably deposited everything down here in this other creek. And unfortunately, you know, because this was such a big storm, this creek was probably running really hard, and it eroded most of that deposition down there before we could get the second set of LiDAR collected. So, looking at the results, this is the 2009 to 2018. So this is mainly pre-fire. We mapped 50 mass wasting events in here. So study outline is in yellow, and all these pink little areas, these are debris flows or landslides that we mapped in this event. So again, this is a 9-year epoch in here, 50 events that we mapped. So if you annualize that, you get about 5.5 events per year. You know, that's really similar to that long-term rate that I was talking about before from the orthophotos of 6.5 events per year. Neither in both of these cases, we don't think there was a large like storm that would have triggered a whole bunch of debris flows and landslides. So we really kind of consider these kind of a background normal wet season type of year. Okay, this is post-fire, first post-fire epoch, 3 years, 202 mass wasting events happened in here. So a lot more events in a lot fewer years. And you can see all those down here. You can see there's just a lot more of them. And what there are, many of them ran out quite a bit further than any of the ones in the pre-fire. Um, Nancy and I did a bunch of field work after these events. And, while we were out there, we found about 16 of these. These are probably all the ones that hit the road or impacted something that we could see. So really, turns out we didn't, doing the field work really wasn't a great way to find all of these. And if you annualize these, you come up with about 67 events per year, which is a lot higher than the 5 to 6 events per year in the previous case. Then the final data set, well, we didn't have quite enough money to purchase lidar again that covered the entire study area. So we did what we could and we covered the smaller portion down here. But regardless, we found 64 events in this case. Again, field work, we found about 23 of these. And if you annualize this, it's only 1 year between the lidar data sets. So it's still up there in the 60 events per year type of rate. Okay, so this data was just fantastic to work with. It was so fun to do this mapping. I just wanted to share a little bit of it, what it looks like with all of you. So I'm going to do just a quick little lidar change analysis tour here. So over here on the left is the lower part of Eagle Creek. Here's I-84. Over here in the Columbia River is just off of this image. But you can see a large deep-seated landslide right here, portions of that reactivated. You can see quite a few shallow landslides. There's one, there's a couple more, maybe coming off of a trail. You can see these longer run-out channelized debris flows that came all the way down. There's one. Here's another one depositing kind of on this very nice-looking older fan deposit in here. Several shallow ones that came down here onto the exit ramp and blocked that exit ramp. We also had at least one deep-seated landslide that moved. In this case, I don't know if you can see this, but there's this kind of big hump that sits right in here. We mapped this as an older existing deep-seated landslide, and this thing reactivated in the storms that we had post-fire. So this is pre-fire, but I want you to look right along here, and what you're going to see is a portion of this reactivate and this tension crack develop across the landscape. The other thing that happened is all this material down here got kind of slowly fed into the creek, and we had debris flows coming down Mosquito Creek once every week or a couple times. I think Mike Zimmerman said this happened like a couple dozen times, so many debris flows, in which case they had to build a little bit of a berm to keep these from going onto the highway and closing the highway. Okay, now I'm going to flip to the next screen, so pay attention in this yellow area. Here's the after case, and hopefully you can see this tension crack that runs all the way across the landscape. The other thing you can see is a lot of this material is missing. I'm going to back up for a second. You can see that material in there, and then go forward. You can see like a lot of that is now missing, and it's because it went down this creek. Over here on the left, I've traveled to kind of upper Eagle Creek, and here's another shot of some, you can see some shallow landslides in there, but this is one of the longer runouts that we saw. And interesting enough, some of these initiation sites here are occurring right along kind of the erosional front of these existing deep-seated landslides in here. Here's one, and you can see these things initiating right off the front of that thing. Here's another one in here. A couple of those look like they initiated off of that. And then finally, to end our tour here, I've turned on the change analysis over here at Mosquito Creek, so you can really see, that upper downdrop block, and then all this material that came out caused some scour in the channel here, but mostly ran out of the channel onto the fan here, depositing material onto the fan, and then unfortunately onto the highway as well. Over here on the left is now Oneota Creek. That's right here. I-84 is here. This is the Columbia River. Just some more of the events that we were able to capture. Here's a bigger kind of almost deep-seated debris flow. Lots of small debris flows. There's one. There's a couple more. couple interesting debris flows into Oneota, and some couple really small little landslides. I don't know if you can see that little guy right there. Using this data, it just seemed like they just couldn't hide from us, like we could find them. It was quite amazing and fun. Okay, so let's dig into some results. So one of the things that we noticed is the style of debris flow initiation appeared to change and actually reverse from pre-fire to post-fire. And what I mean is that we had more shallow landslides than we had in-channel failures pre-fire, and post-fire we had less shallow landslide initiations and more in-channel types of initiations. And what this really suggests is an increase in runoff and a reduction in the kind of infiltration initiation of debris flows post-fire. So what else happened? Well, one other thing we looked at was the contributing area above the debris flow initiation sites. So over here on the map, what I'm talking about is where the debris flow actually initiated. In this case, it's an in-channel failure. There was some erosion in the channel above it. Below that, this is debris flow transport, and then there's the deposition that occurred. And the contributing area, what we did was we just used these polygons to establish as kind of a pour point, and boom, in ARC, we can easily establish that watershed above there and then examine that watershed. And what we found was pre-fire required a lot more of that area than did post-fire. Post-fire required about 50% of that contributing area. And again, that may be an indication of kind of increased runoff post-fire versus pre-fire. So some other fire effects, we looked at the DMBR at these sites, and one thing that we noticed was that, yeah, a lot of the sites were in this kind of low, moderate, or moderate to high burn severity, but we also had quite a few sites that are down here in the unburned category. And what that likely means is that it rained hard enough that some of the sites that weren't burned initiated as well. We know this area is very prone to debris flows. So we probably had some effects from the fire and some effects that from areas that weren't burned. We did look at 121 of the in-channel style debris flow initiation sites, and we looked at that contributing area above that initiation site with regards to, was there the combination of both very steep slopes and kind of above moderate burn severity, which 270 is kind of this cutoff here. What we found was that 68% of the sites had 50% of this contributing area with both of these factors. The other thing that we noticed, though, is 15% of these sites had 0% of the contributing area with both these factors, which likely means these sites, really initiated without anything to do with the fire. Okay, so now we're going to look at the event, the Levens Creek fatal debris flow, in a little bit more detail. And one thing we did was we made a poster out of this, which will come with the publication. And the poster kind of shows the track of the debris flow here. And then it has these profiles down below that all kind of match up with variable factors changing along the debris flow path. And so what I'm going to do is we're going to start up here, and then we're going to walk our way down these profiles and look at how these geomorphic factors change and the characteristics of the debris flow change as we go down the path of the debris flow. So first, I'm going to zoom in to Dotson-Warrendale. It is just a really unique spot with these huge debris flow fans sitting in here, all kind of coalesced together. You can see all these paleo channels in here. The geomorphology in here is just really rich and really interesting. So these are some of the events that we mapped in here. Some of these, they're showing red as if the ground moved down in these areas, but these deposits were removed by ODOT. And so before we could collect a second set of lidar. So that's not really what happened. So I'm going to zoom in a little bit here and kind of lighten up that hillshade so that we can look at this a little more. First thing you probably notice is there was a lot that happened in here, not just this event that came down and this caused a fatality and it closed the road. So we absolutely knew about this. But up here, a lot was happening that we just didn't know about until we were able to do this analysis. A lot of smaller debris flows coming down these and depositing onto these smaller fans that are kind of sitting on top of these bigger fans. A lot of shallow landslides. Here's a shallow landslide. A couple of these shallow landslides are kind of feeding material into these channels. In this case, a channel that didn't have a debris flow, probably loading this channel up, filling it up for the next round. In other cases, smaller debris flows coming down areas with smaller basins. So now we're going to zoom in on this one. I'm going to take this debris flow and I'm going to flip it to its side. I'm going to turn it 90 degrees to the left. And so now we're looking at it. So now north is should be facing left on your screen. So the upper plateau is up here. First thing we did was we filled in that deposit area with data that we collected from the field. So now you can see it's all blue in here. That means the ground has gone up. Second thing we did was create a profile line right down the center of this path, all the way from the river up to the plateau. And then the third thing we did was divide this landslide into segments, 100-foot segments in this case. And those segments are what we're going to really look at. And it's really interesting that we can look at this, not only change in time, so the LiDAR data sets, but also change that's happening along the path of this debris flow. So up in the upper parts again, we have kind of this almost beautifully shaped cone up here, bedrock. Hollow that's up here where it was probably mostly runoff taking place. There's very little soils on the ground here, mostly bedrock. And so we're probably having a lot of runoff in here. And like I said, we noticed what looks like some erosion in the channel itself. Then we have the debris flow initiating right here. And we were looking at this photo straight on. Now we can kind of see it. And here's that waterfall that we were looking at before. And there's that debris flow initiation site. Then the debris flow comes down this tributary channel and then runs into the primary channel right here. And you can kind of see that on this helicopter photograph. Comes down here, meets the primary channel, and then keeps going down here towards I-84, Highway 30, and there's the Columbia River. So we keep kind of walking ourselves down this path. Comes down the primary channel, and right here it meets the apex of the fan. You can start to see deposits even right along here from past debris flows, and then it kind of gets out onto the fan a little more, and the levees begin to form. Here's that first levee that forms. You can see that quite beautifully in this ODOT helicopter photo. And then it keeps running across the fan here. Those levees get more developed, and it gets down here, and the erosion kind of stops, and it's 100% deposition from here on. At one point, it looks like it kind of bifurcated. You can see this lobe over here. You can see that lobe over here in the photo, and very fortunately, that didn't continue on because there's houses right below that. Most of the debris flow kept going down this main path and then kind of filled up this whole basin in here, bearing Highway 30 and going out onto the interstate. And this deposit in here was, probably at a maximum like 15, almost 20 feet deep. So it's really big and deep, and it's hard to tell that on this image, but there's a car right there so that you can see kind of how big this deposit is in here. Okay, so now I've kind of walked you through these zones along the debris flow path that are down here at the bottom, kind of this contributing area zone, the channel erosion, then the debris flow starts right here. We have this tributary channel zone down here. Then we have the primary channel zone, the fan apex, the levee zone, which is out on the fan itself, and then the deposition zone. And this little kind of bar across the bottom, I'm going to keep that with us as we go through the next couple of figures. to kind of help us keep track of what zone we're in. So first we're going to look at the geomorphic factors. In this case, we're looking at relief, geology, channel gradient, which is this middle one, and confinement, which is this lower one. And so up here, you can see the relief, almost 3,000 foot of relief in here, very young volcanic deposits up on top with hardly any soils on them. And then we have Columbia River basalt underneath that with quite a bit more colluvium on the slopes as you get down in here. That colluvium just tends to get thicker and thicker as we go down. And then we're kind of on the fan, and some looks at some water wells that have been drilled in here indicate this fan deposits down here are really thick, over greater than 50 feet thick in here. And then the second one we can look at is the channel gradient. And this paper down here kind of established 3 different zones, high, moderate, and low, for channel gradients. And those are related to whether or not debris flows will keep transporting. So you can see we put those on this graph here. Up on top, the gradient's really low on that flat plateau. You come over that edge and it gets really steep. Then we have that vertical escarpment where the waterfall is taking place, and boom, here's where the debris flow initiates. Gradient stays really kind of high. This is like 35 degrees in here, so it's really steep channel in that tributary. Then we go through the primary channel, it stays really steep. We get onto the fan apex, and it's still pretty steep. And it isn't until you go out on the fan a ways till that gradient kind of dips below moderate, and then kind of wiggles back and forth, and then really drops. The gradient really drops when we get into that deposition zone. And then down here is confinement. Again, this paper kind of organized 3 different categories, low, moderate, and high. And those are on this graph as these dashed lines. So up on top, completely unconfined. You go over that edge and immediately becomes very confined. And then kind of get into that tributary channel, and the confinement kind of goes up and down, actually pokes down below moderate for a second. But when you get into that primary channel, there's very steep banks on both sides. The confinement stays very high in here, and then slowly the confinement starts to go down as we go across the fan apex, and then we get out onto the fan, and the confinement continues to drop quite a bit and then goes down to low or none. So let's see how these geomorphic factors affect the debris flow characteristics along the same path. So now we're looking at erosion and deposition. That's this top graph here. Growth rate, that's this middle one. And then volume passing is this last one. So we can see kind of in the erosion area, we had maybe up to 5 feet or so of erosion. Debris flow initiates right here. It's really digging in. We have these are maximums on both cases. So you can imagine more averages being somewhere in here. So now we're down 5 feet, 10 feet deep. When it gets into that primary channel, it's really digging down. This is 15 feet of topography difference. And then at some point it gets all the way to about 20 feet, and that's right at the fan apex here. And then it slowly starts to decrease until we kind of get to where the levees start forming. So now we got deposition and erosion taking place. The levees are forming in here. We're still eroding all the way to right here where it's only deposition in that deposit area down on the road. Again, because all this data is digital, makes it really easy for us to draw a cross section through this profile. So let's take a look at what it looked like at BP prime. So here down at the bottom, we can zoom in. So now we're kind of out in that levee zone. Here's BB prime, and the debris flow is kind of going around a little corner here. Here's those cross sections. Again, before is in blue, after is in orange. And what you can see is a smaller levee developed on this side, on the BB prime side, that's over here, and then a much larger levee developed on the B side over here. And, as this thing was kind of going around this corner, it kind of super elevated over on this B side as it was probably going around this corner. You can see this dashed line probably indicates the maximum flow thickness that we had in there, which is again about that 20 feet. And that's where this 20 feet comes from. The other thing you can notice is like most of the erosion was taking place on this outside bend here. Okay, so now let's look at growth rate. And, the one main thing we noticed is that the growth rate constantly changed along the entire debris flow path. Like a lot of what we do is we establish a growth rate, a single growth rate for individual channels or even regions. And what we found was, well, it actually doesn't stay the same. It changes along the entire path. You can see it starting lower and then growing. The growth rate increases as you go through the tributary channel. It really kind of comes to a maximum here while we're in that primary channel zone. And then the rate actually is decreasing, but we still have growth taking place way out onto the fan. In fact, all the way out to here, which was kind of a surprise to me. I thought the growth might stop somewhere back in here as we kind of leave the mouth of the channel, but nope, it kept going here. And we'll get back to that in just a minute. And then finally, the overall kind of passing volume, you can see is really matching these, the erosion depths and the growth rates that are taking place. And the one thing to notice is how steep the curve gets as we go through this primary channel. That's where the growth was really taking place. Okay, one thing we could do with this growth is maybe establish zones of growth. For example, maybe tributary channel, we could use a mean growth, primary channel, a different growth, and then out onto the fan, maybe a growth, and so on and so forth to do a better job at modeling in the future, which I'll talk about in 1 second here. So getting close to the end here, this is the volume that I wanted to show you. So we came up with 48 1,000 cubic meters of volume in this event. And if we look at the 96 event, it looks kind of like this. Ken Cruikshank, a professor at Portland State University, did a very detailed map of that 96 deposit. And, the one thing to notice is this deposit, this one pre-fire went further and was actually quite a bit bigger than that one in 96, of which we know the total terrestrial water input was quite a bit bigger for this event pre-fire than it was for this event post-fire. So getting close here to the end. So why do some of this detailed quantitative analysis? Well, we have a kind of a sister project going on right now where we are making susceptibility maps for this area. And when you're making debris flow susceptibility maps, one of the things you do is kind of establish a pour point or the outlet of the basin, right? That defines kind of the basin above which you're modeling. This black outline is the 2021 debris flow event outline. And we put the pour point right about here, kind of close to the outlet of the basin. And we ran our model, which we're using Reed, Coe, and Bryan's model from 2016. And we ran the model and it kind of produced this hazard zone that ended right here. And we went, oh, shoot, that ends too soon. And so very fortunately, we had done that analysis looking at that path. And what we saw was that the growth really didn't end till way down here. So we took that pour point and we moved it way down here. We reran everything with the same factors, and the model results look, as you can see, much better. Just getting that kind of pour point in the right place, which also defines the end of growth. So if you have it here, it's going to stop growing, and then you just get kind of run out, and that's why it stopped here instead of having that pour point down there. So really enlightening for us. Okay, so some summary here. We think wildfire really has an influence on debris flows in Western Oregon, and continued research is really needed. This is really just a start at this for us. I think. The initiation process really appears to be different than we see in these drier climate post-fire response. We're not seeing this primary runoff kind of slope rilling style initiation of debris flows. Although we saw some of them, but not kind of consistent and overall. What we did see is a change from a more infiltration dominated debris flow initiation through shallow landslides to a more runoff dominated in channel. The other thing we saw was well between the background rate, which probably isn't surprising, this non-large storm background rate that's about 6.5 events per year compared to pre-fire, compared to post-fire with large storms. Well, the increase went up quite a bit, tenfold in this case on an annualized basis. So some other just summary conclusions. Well, high resolution multi-temporal airborne lidar provides an objective, continuous, quantitative, detailed inventory data set. This is the future. I think, and many people are going to continue to start to continue to work with these data sets. So again, 266 debris flows found with the lidar change versus 39 that we found in the field. That means we only saw 15% of what was really happening out there. And I think details from this type of analysis are really going to help in the future with modeling. For example, understanding pre-failure conditions, variable growth rates, where to stop growth, and where and how these debris flows initiate. And with that, I would be happy to take any questions or comments.